Hey, John here. I've been looking at some of the comments in the Discord from people that are building the Z80 Retro, and some people have commented they can't always find the SRAM or the flash chips in stock. A quick shout out to all my Patreons, especially the VIPs. You've been incredibly generous. I am touched. It's wonderful. Thank you for your help. Now let's look a little more closely at these two chips. The ones that I chose, the AS64, C4008 for the SRAM and the SST39SF010 for the flash chip. We can substitute different chips in here if we want to. Now let's start with the flash chip. Notice that there's three different ones here. There's the SST39F010, the 20, and the 40. Look at how the pins and stuff on this chip work. If you get the 10, pin 1 is ignored. NC means not connected. It doesn't matter what you do with that pin. It's irrelevant. Pin 30 over here is also not connected. And this is the key to the whole thing. Now let's see what I did with pins 30 and pin 1 in the schematic for the flash chip. Pins 30 and 31 are marked no connect, and I connected them both to ground. And now you can also see this fat line right here, and I talked about this some time ago when I did a design revision on the Retro circuit board, because people were asking me, to see if I could make it easier for them to hack the board. So I put these in here. Those are net ties. Now, if you didn't watch that episode yet or you missed it, you should, of course, go back to it and oblige all the advertisers on YouTube. Moving on. Okay, so let's look at the flash chip here. Pin 30 and pin 1. You see these big green blobs on there? Let's look at the 3D view of the board here. All right. This being the flash, we can flip this thing over and we can zoom in on it. Oops. Pin 30. Actually, that's pin 1, rather. And pin 30 is over here. So if we zoom in really close on this thing, you see how this has this little copper stub on it there? What's happening there is this pin, I specifically designed to allow you to go in here with an X-Acto knife and cut this if you want to. And that pin would become unconnected to anything else in the circuit. So you can put a little wire on here and connect it up to whatever you want. Same thing is holding true over here with pin number 1. All right. Now, fortunately, we don't really have to do this for the specific modifications that I'm going to talk about in this video. However, if you use different kinds of flashes, and one of these pins needs to get pulled up to 5 volts instead of connected to ground, that's one way you can do it. So, what does that really mean to us? Well, if you go out and you find out you can't buy a FO10, but they do have a 20 or a 40 in stock, and of course in the right package, all right, then you can just simply stick it in there. Because if you used an 020, A17 on the 020 that doesn't exist on the 010 would simply be connected to ground. It would be pulled low. You just use the lower half of the chip. Now, let's say you can't find a flash PROM at all. And maybe you have an EEPROM programmer or a friend that has one. You can use one of these. Now, you got to, of course, be careful. These are pretty old chips. They may not run very fast, but they do have some that will, namely this one right down here. This one's rated at 70 nanoseconds. It's a little slow for the Retro, but it's probably okay. And I've got word from various people on the Discord that claim that they've even used, 150 nanosecond ones, and they're having no trouble. So your mileage may vary. Let's see how these match in terms of compatibility, all right? Now, this has a VPP over here on pin 1, but otherwise these are all the same. Let's see if we can get both of these on at the same time. That'll be more useful. Maybe move this over to the left. All we really got to do is match it against the FO10A there. Okay, so here is a UV erasable EEPROM and the FLASH EEPROM that I'm using now. So what do we got here? 1 through 16, same except for VPP. That's okay. We'll see in a minute. We've got 32 as VDD. This one's VCC. That's two different words for 5 volts. We have a P bar and we have a WE bar. We got pin 30 no connect. We got 14, 13, A8, 9, and 11 are the same. We got OE there and G bar here. We got A10 and E bar versus CE bar. These are different names for the same thing. This is active low chip enable. This is a chip enable active low. G bar here means basically the same thing as output enable bar does over there. So these are all the same up to A14. And then what do we got? The no connect. We got the right enable. It's this. And this is P bar in the UV version here. Now, the UV version, you need a very special programmer. It has to have a different programming voltage, like 12 volts or 24 volts, and you have to control the program by diddling around with pin 31 here. So you can definitely not program this with a Raspberry Pi adapter like you see me do with my flash-based EEPROM. However, if we look up the specs, like I said, if you have a way of programming one of these, you know, the giant question becomes, will it work? And the answer will be yes, provided that E bar is the same as CE bar, and they are. G bar has to be the same as OE bar, and we'll see that those are. We need to make sure that we can do something reasonable with pins 31 and 1, like hopefully we can just simply leave these connected to ground, like I just showed you on the circuit board. Now, if we come down here and it looks at, where are we going to see? Here's what we've got here. If you want to read from this chip, E bar has to be low. VIL means the input voltage low. Okay, G bar has to be low. Remember, this is the enable and the output enable. They both have to be low on the flash, which matches the UV EEPROM. This X over here means I don't care what's on P bar. Now, generally speaking, it would be nice to make sure that it's not out of the 0 to 5 volt range. But other than that, you know, you need to make sure that's okay. It also says I don't care what's on A9. A9 is used as part of the electronic signature. It's not to say that it ignores A9. It just simply means A9 is a regular address line during this time period of operation. Now, it will say the output will be disabled if G bar goes high, even if E bar is low. Okay, so what is it? Program inhibit standby. If you raise E bar, this means it'll go into a low power standby. This one up here means it will be online and it simply will disconnect its output. So all we really care about is as long as these two here are both low, we'll get data out of the EEPROM. And if either one of these really goes high, you won't get data out of it anymore. And the other takeaway is that P bar is a don't care, because we're not going to use programming verifying in the signature. None of this is done in the retro. It would be done presumably in your programmer if you had one suitable for programming that chip. Back to our main circuit here. We can clearly see that these pins aren't numbered, but 5 and ground are compatible with the UV erasable EEPROMs that I was just showing you. And pins 30 and 1 should be fine when they both go to ground, right? So the CE and OE on the flash, which is your E bar and G bar on the UV erasable EEPROM, they have to both be low in order to read data out of the flash. We talked great length about the flash MREC and how that all works before. So pin 31, which is the program pin for the flash, this will be going high and low over the course of time. And again, I believe that's the P bar pin, which means it doesn't care what we put on there. P bar. Is that the pin 31? So, in conclusion, if you find yourself in need of an alternate way to boot your retro board, and you have a programmer or have a friend with one or whatever, you can use one of these things, provided it goes fast enough. The Dash 70 is fast enough, from what I've been told. Now, be very careful, because a Dash 12 is not faster than a Dash 70. The 70 will run at 70 nanoseconds. The 12 runs at 120. The 15 runs at 150. Okay? Are you following me? The 10 is going to be a 100. So they didn't expect anything to go faster than 100, I guess, when they first designed these. This one's going to go at 200 nanos. All right? So don't get confused by how they number these chips, okay? Get the 70 or get one that someone else has already verified as maybe they're not rated well, but they work acceptably in another retro that's running at 10 megahertz. And it'll work. Just pop that thing in there and fire it up. Now, let's talk about the static RAM. Some people have mentioned they couldn't find the static RAM either. Well, it turns out that when I designed the first draft of the retro, I mean, those of you who have been following all along since day one, I don't know. I'd have to actually go back and re-watch some of the videos myself. But I know the very first version of the retro, the prototype, did not have a 512K SRAM in it. It had 128K SRAM in it. And I still have some of those chips around, so we can verify that they still work in the retro. Now, I happen to know, out of the box, right now, today, with the code that's in GitHub, they will not work. And the only reason that they won't work has to do with something that happens in the boot flash. That's just a software issue that we can change and make everything compatible. So let's go over the exact code change that has to happen and take a closer look at the 128K static RAM that I started with, and we'll verify it right now because I got the chips in stock. The short of it is, there's SRAMs that only have 128K don't have A17 and A18. They go up to A16. That's as far as they go, all right? So the real question then becomes, what are these two pins doing, and are we compatible? Just the same kind of question I had with the flash. What's going on with pins 30 and 31, and are we compatible, right? So it turns out while the flash is compatible as it is, no changes, just stick it in there. The SRAM, not quite perfect. So here's the data sheet and the pinout for the original 128K static RAMs that I was using, okay? We'll see that all the pins are the same, like I said, except for A17 and A18 in the schematic are not present on this chip right here. One of those is on pin 1, and it's not connected on this SRAM, so it doesn't matter what we do with it. It turns out that's A18 right there in this schematic here. Let's get them both up here on the screen. Pin 1 is A18 on the 512K. It's not connected at all on the 128K. Not a problem. A17 goes to pin 30 on the 512K, and pin 30 on the 128K is connected up to a signal called CE2. So as long as CE2 is satisfied, this chip will work. Let's look more closely at what CE2 is supposed to be used for. Here we go. CE bar, okay, and CE2, OE, and so on. Now, these are all going to be the same as the 512K. What do we got to do to make this thing work, right? We're in standby mode, output disable. We want to be able to read and write from this chip, okay? It turns out in order to be reading or writing, CE2 must be high, and CE bar must be low. Well, it's not a shock about CE bar. That's compatible with what we've got now. However, what we have now for CE2 is connected up to A17, and A17 is driven by our bank select latch. So if A17 has to be high in order for the SRAM to work, then we need to make sure there's a 1 there, because A17 here at 30 is connected to CE2 over here. And that's all we got to worry about. Now here's the new diagram after we did the direct map cache, right? We went over this before and at great length early on. On day 1, the original design, we used bank 0 and bank 15. Each bank is 32K of RAM. The thing addresses a total of 64. So bank 0 was the low half of the memory from address 0 to 7FFF. And bank 15 over here, which, as I've shown this before, I copy up here in order to get kind of a mental picture of this, starts at 8,000 in hex and goes up to FFFF from the perspective of the CPU, okay? Now, we need to make sure that A17 is always a 1, otherwise this smaller RAM will not function. And clearly, if we choose bank 0, which means we have 0000 on these 4 pins, A17 will not be high, and the SRAM will be shut off. So if you do that, there will not be any memory enabled in the system, okay? Don't do that. We can only access banks when A17 is a 1. And for a mental simplicity, let's just say 18 is 1 and A17 is 1 at all times. As long as that's true, then the system will function properly and normally, as we would recognize, okay? So that means that bank in hex, if these is a 4-digit number, 1100 through 1111 would be the banks that we could use. Well, this 1100 is a hexadecimal C0. And all ones is an F, right? So as long as the banks are always C0 or greater, we're good. Okay, so that means the last 4 banks out of the 15 total are the only ones we can ever use. Now, we're gosh darn lucky that bank 15 is part of the 4 banks, right? Because that has to work. Otherwise, we can't use this, right? Because we hardwired it with those OR gates. The upper half of memory must be mapped to bank number 15, always, all the time, no matter what. It's not an option. You'd have to pull up the traces on the board and redesign the board, how the board works, and if you want to change that. It's hardwired in, okay? So that's not a problem. We need to make sure that bank 14 is used for the low half of memory. And like I said, we already made that change when we added the direct map cache. But we made that change to the BIOS code. We never made the change to the boot flash code. So if you use this 128K RAM chip in a Z80 Retro and you use the current flash boot code, it won't work because it's trying to write into bank 0 and the whole Retro will crash if you do that. So all we really need to do is make a small change to the firmware code. So what is the change, you might ask? Well, remember how this thing works. First thing it does, literally the first thing it does, is it goes out and grabs a value, which we call the GPIO output cache, and it writes it into the GPIO output latch. Notice this comment, select SRAM low bank number 0. That's the problem. And idle the SD card and the printer signals and so on, right? So this value here comes from the very end of the file, and it's initialized to this value right here in binary. Okay? MOSI is high, SSEL is high, and the print strobe is high. Well, if we go down here, that means MOSI, SSEL, print strobe. That's these pins up here that control, like, the SD card and the printer and all that. These 4 are 0. what we want to do is set these for, preferably, to match what we do in the BIOS once we jump up into the BIOS code anyway. And what that does is it sets it to an E0, which is 14. That's what we did when we changed over the code in the BIOS to support the direct map cache. Now, keep in mind, if you use this smaller RAM, you don't have these banks down here where we normally put the cache, so don't come yelling at me if your direct map cache stops working, because it can't work, because there won't be any memory down there, okay? So, short of it is, don't try to do this and enable the direct map cache. It will not, cannot, and it's not going to work, okay? So, if you can't find a 0.5 mega RAM, you go with the 128K. We can go in here. Actually, it's quite simple. You can just simply say OR it with hex C0. Done, okay? Now when this thing boots up, it'll boot out of bank 14 and 15 instead of 0 and 15. Well, 14, I'll change the dock so that we're not too confused a year from now and I forget what I've done. And all is well. So here's my retro. This particular SRAM right here is 128K. This is the one I just took out of it. It's got 512K on it. Let's make sure that the thing boots up and still works correctly. Let's put the latest copy of the bootloader in the flash by setting up my Pi programmer here. So let's go ahead and compile this up. Look at the README file, and we have our Flash Programmer app here. And hopefully everything still works. Now I upgraded the software on my Raspberry Pi. I think I did that in a couple of videos ago. And when you do that, they like to destroy all of your local custom settings, one of which is make the I2C go faster, and by default, it's agonizingly slow. And I have yet to go back in there and fix it, but we can get over it. This is really a problem when you're doing a high iteration, edit, compile, run, loop, and you're constantly programming the flash. You would like it to go faster. But once in a while, once every 6 to 8 months, I can live with it. Now, I'm going to reach over and hit the reset button. And that is good news. Okay? Now, remember, this is not using the direct map cache. Obviously, it wouldn't be working if that was the case. This one's currently running the in my NHEP get status. Yeah, I'm in the NHACP branch over here, okay? So this is running, some code under development. But what I'm going to do right after this video is release this into the main branch so everybody gets the new version of this code so that you can follow along before I get all my other fun stuff ready for public release, okay? So I repeat, here's the data sheet for the RAM that is in the retro right now. It's an AS6C1008, which is only 128K, all right? Now, when you're running with less RAM, keep in mind that if you're trying to run an app that's using any of the bottom, 12 banks, it's not going to fly, okay? But it'll get you going. And certainly be able to run yourself a 16 drive and anything else that you've seen me do ever, except the cache, the direct map cache code. That'd be the only thing that I've done so far on this channel that won't work with this SRAM. And as you can see, we've got 9,500 in stock right now on DigiKey, so this shouldn't be a problem. Now, while I'm here, what we should do is have a look-see at the other RAM. And it also just so happens that at this very moment, we also have the 512K SRAM in stock with 3,800 units. as well. So this may not be a major issue today, but it's been on again, off again. People have expressed concern that they couldn't get them. So now you have two options. Now, I don't have any of the EEPROMs hanging around for me to test, but I have it on word of mouth, and I have more than one person who have confirmed that EEPROMs, the UV erasable EEPROMs, are working fine. If you go to the Z80 Retro Discord channel, you'll see a lot of people in here that have been talking, among other things, where serial port cables and assemblers, disassemblers, all kinds of stuff. Different things. Here's somebody who's got an alternate video solution. Here's other people, different kind of cases for various machines. And, there's a lot going on in here. So if you type in, I want to search for something, and I type in EEPROM in here, and I say enter, we should see some stuff. Well, there's something that I even posted right here. Oh, I guess if you click on it, it zooms to that posting in here. So I was actually talking about something that I did 30 years ago, and there's a UV EEPROM and some other stuff. But people got to talking about EEPROMs. Here's Toby Dog. A couple of days and yada, 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 and I've got some EEPROMs in the shop. So if you look around, here's another one, Trevor Jacobs. I have an EEPROM burner, blah, blah, blah. Here's another one. I've never tried them with John's Retro. And these are from a month ago. Don't waste your time and money with China. Yeah, blah, blah, blah. Get yourself a CO10, pin compatible from Jameco. So here's somebody confirming that these would work. Lead time is too big, and he couldn't find them at least a month ago. Here's somebody else. Here's something like this. And again, we were chatting about this. My point is, some of these guys have a whole bunch of them. And if you go through here and read, well, first of all, they'll tell you, here's a program that I know works. This one works on Linux. This one does not, and so on. Look in these threads in here if you're stuck and you're sitting there and you've got your Retro, but you don't have an EEPROM. So here's Trevor saying that he just bought one. He said he bought a grab bag. Yeah, this is the posting that I thought of in my head when I was talking about this. So he just programmed up a bunch and they were working. And I think that comment started a lot of other dialogues with some other people that have EEPROMs that they were verifying that they're working. So if you want to go this route, send some of these people some notes. They might be able to program for you. They might be able, and well, in fact, I have seen people, offering to program them and mail them to other people. So if you're one of the people that are trying to build a Retro and you can't get a useful flash here, or any of the larger variations of these things that I've never used, but I know they're going to work because they're exactly the same manufacturer, the same pinout and everything else. And these pins are both grounded, which is critically important, by the way. The Pi programmer will work provided that if you use an 020 or an 040, you want pins 30 and pins 1 to be low. And the reason has to do with, in order to program this chip, you have to access memory with low addresses. Okay, and that means that you have, when you're programming it, you have to have 17 and 18 low in order to get it into the programming mode. Okay, so this will work fine on the Retro if you can get any one of these three sizes. So it'll also work fine if you get a hold of some of these people that have one of these EEPROM programs. Here's somebody who sent a photo of it working perfectly fine, he says. So these will work if you can get them and you can program them. So this is a great place to get that information. So there you have it. We have an alternate way to get flash chips, or at least the EEPROMs, right? And there are people that I know on the Discord that would be glad to make them available to you. We can also substitute different SRAMs, right? You've got a couple of options on both of these now. So hopefully this will help some of you forward. And I will, before this video is available on YouTube, I will push up the modification we just looked at in the boot flash to make sure that both of the SRAM sizes will boot. Okay? So, thanks for watching. Let me know what you think. I'll see you next time.